what I want to do here is to talk about adding space to foot and mouth and avian influenza models. And I originally planned to record this as a single video, but I think this would be a very long video. And so instead of doing that, I'm going to split things into three um, shorter videos so that at least you don't have to watch a single thing and you can sort of take breaks in the middle. Um, the way I'm going to split things is that I'm going to first talk about this first aspect, and this is going to be this video. Then in the next video, I will talk about metapopulation models that are a way to incorporate space into mathematical models. And then I will talk about a few foot and mouth disease models and a few avian influenza models in a third video. So the first thing that I do want to cover is this incorporation of space into models and why we should do that. And in terms of explaining this, what I will do is I will first go through some examples. Um, The first thing I'm going to detail a little bit is some general considerations about space and time spread of infectious diseases, and then talk about very briefly spatial aspects in animal diseases in general, and then talk about foot and mouth disease and avian influenza. That would be the object of the modeling exercises. Uh, First of all, I always start lectures about the spatial temporal spread of infectious diseases with this quotation from Thucydides, who's this guy here. And Thucydides is considered one of the first historians. He lived in Athens between these dates, and he, in this quotation that I'm giving you, discusses the arrival of plague. It's actually not really a plague, but of a plague, so-called plague at that time, in Athens. And what you can see is that there is this description of the spatial temporal aspects about this plague. So the disease started in Ethiopia and then descends into Egypt and Libya, and then in Persia, and then it arrives in Athens. And in Athens, it actually attacks the population in the port of Athens, and then moves towards the upper city. Um, and so you can see, reading this, that there is a interesting description of spatial temporal aspects. And that was about 2,500 years ago. So it's not something new, and I like to point this out because it shows you that this is a problem that has occupied people for quite some time. Now, if we fast forward about 1,500 years after Thucydides' description, these are illustrations of trade routes in Europe and the close and Middle East in 1212. And so you can see that this is showing you the Silk Route. I don't know where my finger is disappearing, but this is the Silk Route here, and goods were arriving. Actually, you can see not only goods, unfortunately, slaves, ivory, but so all these so-called goods were arriving into Europe following these trade routes. And the reason why I'm illustrating this is that if you fast forward 100 and something years from that, what you see is the arrival of the Black Death into Europe from essentially following the same patterns as that pattern of trade that we saw earlier. And at the time, it took, actually, this is cut off at the top, the plague arrived in Europe in 1347. This is where it hit the south of France and parts of Italy, and then it progressed throughout the continent over the span of 3 to 5 years, essentially, in a variety of um, waves, subsequent waves of spread. Um, and this is a very important event. It's an important event because we have some records of what happened at the time. So we have a good understanding of this wave. And also, there's a variety of aspects that are important. So it's the first of the Middle Age plagues that hit Europe. It started in Afro-Eurasia essentially in 1346, and it hit Europe, as I was saying earlier, in 1347. It killed, and of course the estimates are quite wide regarding this, but it killed between 75 and 200 million people altogether during the course of these 6 years of spread. And more importantly, I mean, importantly in the sense of to give you a sense of the impact, it killed an estimated 30 to 60% of the European population at the time. So if you put this in context with COVID, for instance, COVID-19, of course, this is an epidemic that had an enormous impact compared to COVID. And you can see the impact that COVID had. So imagine if you lose essentially a person out of two um, about this. I heard recently, for instance, someone who was explaining that family names in the UK, and I'm imagining in other places in Europe, but the person was discussing the UK and was explaining that family names started to be used around that period of time because it used to be that people cultivating fields, they cultivated very close to home, and essentially you were, for me, for example, I would be Julien from that end of the village. But with the enormous mortality at the time, a lot of people that had areas to cultivate had to hire people from further afield to come work in their fields. And so it wasn't sufficient anymore to say, well, it's that Julien from the house over there. You had to start giving indications, and that's when people started using names. And that's one of the reasons for this. Um, so really an enormous impact. What I find interesting, and I like to point this out as well, is that if you look at the control measures that were taken at the time of the plagues, and that is later, but you know there were plagues in Europe for essentially 300 or 400 years. Uh, the control measures that were taken to deal with the plagues, they're very modern. If you look at it, Dubrovnik in 1377 introduced lazarettos, which were places where travelers from outside of Dubrovnik had to spend 30 days in that case, in order to make sure that they were not importing a disease into Dubrovnik. Later, about 100 years after the first large plague, Venice put in place a system where you had to spend 40 days, so 40, quarantena, in quarantine. So that's where the word comes from, and that comes from the era of the plagues. And it's still used, as we saw during COVID. There were also isolation of known or suspected cases, as well as persons who had been in contact with them for 14 days at the beginning, and then that was increased to 40 days later on. But again, isolate contact tracing and isolation of contacts. There were also improvements to sanitation. They developed pure water supplies, garbage and sewage disposal, food inspection, and so on and so forth. So all of that really are things that were still used essentially during COVID, for instance. And I'd like to bring this up because nothing changes also in terms of the quacks, let's say. One of the things that was recommended at the time was to find and kill a snake, chop it in pieces, and rub it in parts over swollen burrows. And the idea was that snakes, it may sort of disappear, snakes were synonymous with Satan, and like attracts like, and so therefore the bad things were drawn out of your body by proximity, well, by similarity um, with this. So still quite a lot of things that we still use, and I think that's I like to bring this to sort of highlight this connection with what was being done essentially 700 years ago. Here is another well-known case of epidemic moving through space and time, and in this case, it is not very mobile, I have to say. This is the cholera epidemic. I don't remember the year that took place in London, and this is essentially considered the first spatial epidemiological study, and it's by someone who is called John Snow, and who you see a map here of the deaths due to cholera. All the little dots are deaths due to cholera. And what Snow realized is that, so here you can see he's marked with little crosses the location of pumps, um, water pumps. But you know, if there wasn't running water, people had to go to the pumps to get water. And what he realized is that most deaths occurred in that particular cholera epidemic around this pump here. So this is the Broad Street pump, and by doing this analysis of the deaths, he realized that if cholera was probably spreading in the water. And realizing this meant that they were able to address this problem, and that led to the end of that epidemic. Now, if you think about the spread of pathogens in space, one thing that I highlighted at the beginning when I was showing you the spread of plague is that pathogens, typically they've traveled, of all times, they've always traveled along trade routes. And I was showing you how essentially the Black Death followed the trade route, the Silk Route, etc., to arrive in Europe. Well, in, let's say, days of yore, in 700 or 800 years ago, the trade routes were relatively simple to understand. There was quite a complication, but things were really much more simple than they are now. And things have evolved a lot since then. So there's in particular an acceleration and a globalization of mobility that has led to really a different situation. So this is a map of Europe, for instance, and that map shows you high-speed rail connections throughout Europe. So everything that is Yellow is connections, yellow and above are connections that are happening at over 200 kilometers per hour. And so you can see that there is a very good connection throughout the continent, not everywhere, but it is taking shape. Um, and that means that people have access to, let's say, from Paris to regions in Spain and in Germany, etc., uh, at with times that are very much shorter than they used to be. And this is a similar situation with China, which is showing you the density of the high-speed network that was developed in China. So you can see with the purple, pink lines are above 300 kilometers per hour. And so imagine this is a very large population, 1.3 billion people, and most people in China live in the east of the country. And so that means that people have access to much of the territory very quickly. Now, one thing, and I should point out, why am I talking about this when I'm on a course about infectious diseases of animals, so livestock? Well, it turns out that livestock is important and interesting. It's a bit different, and I'll come back to that in a few minutes. Livestock is a bit different from typical animals because their travel patterns, they do travel, and the travel that is taking place is very similar to the travel of humans. So thinking about the way humans move about is illustrative also of the mechanisms of the ways that animals move around, livestock move about. Of course, they don't go on high-speed trains usually, but they follow the same type of routes. Now, one thing that I want to point out, and it's valid for animals as well as for humans, is that when you're thinking about the spatial and temporal spread of an infectious disease, you have to take into account that the human world, in which livestock are also implanted, is one that is jurisdictional in nature. Okay, so there are political divisions at various levels. So, for example, you can have nation groups such as the European Union. You can also have nations, provinces or states, regions, counties, cities, etc. And what's important here is that when you're thinking about whether you're looking at the movement of humans or the movement of livestock, the travel between jurisdictions is sometimes complicated, or actually sometimes even impossible. But also, what's important is that the data you can obtain about several, whatever disease you're working on, that data will typically be integrated at some jurisdictional level. So you thinking about Canada, for example, we will have the data at the country level. We might have that for animal diseases. Typically for human diseases, we don't. We have data at the provincial level in Canada. In Europe, you have data at the country level, or sometimes it will dig down into a finer level of detail, but essentially things are working at the country level. And it's also very important that the policy that might be applied because of a disease. We'll see that, for example, with foot and mouth disease. The policy that is decided at some jurisdictional level. So a country typically, but it can be a narrower, a smaller jurisdiction. It varies a bit. Okay, so it's important to uh, bear in mind this. When you're thinking about space, you have to think about space in its coverage of the Earth, essentially, but also of the geography, the human geography that is underlying this dispersion of people and animals. And that human geography involves jurisdictions, which um, implies specific problems. But altogether, when you're thinking about health, mobility is something very important to take into account. So here I'm talking about humans, but I could very well be talking about livestock, and the problem would be very similar. Okay, so here I'm illustrating things using humans. So when you think about the way humans travel, well, when they travel, they carry with them their health history. So that means latent or active infections they may have, so such as tuberculosis, polio. I'll come back to polio in a while, but also what type of immunization schedules they've been subject to, because that can change by country. And when you're thinking about livestock, the same thing is true. There are countries that are going to vaccinate against certain diseases and other countries that are not. Health and nutrition practices are important as well. I always give this example as someone who lived in France at the end of the 90s. I am not allowed to give blood in Canada because it's considered that I might have ingested prions, which means that I might have at some point Creutzfeldt-Jacobs variant disease, and so I cannot give blood. And that is something that, as a migrant to Canada, I took with me. Treatment methods also vary from country to country. Um, there was a problem when people were working on the preparation of the what turned out to be the 2009 influenza pandemic. We There was a fear that the use of antivirals would perhaps lead to emergence of antiviral resistant strains of influenza. And we knew that different countries had different policies in terms of how to use antivirals. Some said, well, we'll use them prophylactically. Others said, we'll use them for curing people that are sick. And that means that when you're thinking about the potential for emergence of resistance, that would lead to different situations in different um, regions. And I like also to point out that, as was made very, very clear during COVID-19, for instance, pathogens don't really care about borders and politics. Uh, they will typically spread uh, regardless. Now, some examples, still sticking with humans for now. I will switch to animal diseases soon. Um One thing that I wanted to highlight is in terms of the speed of spread. So this is a map of the different countries that were affected by by SARS-CoV-1 in, um, and that's the situation at the end of 2003. So I have China in black there because this was the source of the epidemic. And then the other colors show you the number of days until the first reported case in the different countries. And so you can see when I was hiding Australia, that's why I made myself disappear. You can see that Australia, Canada, and the US imported the disease relatively soon, Southeast Asia as well, and then it took a bit more time for several other places, but in the end, most of the spread occurred within a period of 2 months. That's the initial spread. The epidemic, of course, lasted longer, but the time at which the different countries imported the disease initially imported the disease was about 2 months. Now, when you think about space, and that's going to be important with animal diseases as well, and actually probably even more important with animal diseases, there's also an aspect that is important. So here, what I was illustrating is the spatial spread, the initial speed of spread. Another thing that we might want to consider in this context is the effect of having various policies in place between neighbors. Um, and we'll come back to that when we're looking at models of foot and mouth disease, for instance. But here, what I wanted to illustrate is a situation that happened in Western and Central Africa in the it may sort of disappear for a second here. Uh, this is the vaccine prevalence, well, the prevalence of kids having received 3 doses of poliovirus vaccine at the, I think this map is for 2004. So what you can see is that there is a heterogeneity of vaccine coverages. They go from about 30%, 35 I think it was in Nigeria, all the way up to more than 80% in Mali, Burkina Faso, etc. And then there's intermediate values in Chad and the Central African Republic. Cameroon is a bit higher, but it's not quite as high, etc. But so you can see that there was some heterogeneity there in terms of the prevalence of vaccination at that time. And now let me show you the epidemic curves of the number of cases of poliovirus in the different countries from 2000 to 2005. So what you can see here is that things were going down quite well until 2002, at which point there's an outbreak in 2003 and 2004, essentially, and then things started to go down again. Okay. Now, what's important with this graph is that I'm not showing you everything. So when you look at these list of countries that I have here, oops, here, what you see is that I'm missing one. The ones I plotted. And you can see it's here. Now I've added it, it's Nigeria. And so what you can see is that the numbers were going down in Nigeria as well. And then there's this enormous spike to 900, more than 800 cases that starts out about that time. Now, what happened then is that there was a province in the north of Nigeria that where some vaccine scare happened. People started to distrust the vaccine. We never know really why these things start, but they happen from time to time in a variety of places. We saw that with COVID as well. So people started to distrust the vaccine, and it got to the point where public health authorities in that province in the north eventually decided to suspend vaccination against polio while they sort of got rid of the rumors, etc. They suspended vaccination for about 6 months. But that was sufficient to generate these cases. And what's important is that these cases, so if you go back to this graph, you had some places here that had good vaccine coverage, okay? Relatively good, and good in all that region. But they nonetheless saw quite a bump in the number of cases. So that tells you that the policy, I was talking earlier about policy being decided at the jurisdictional level. So here policy was decided at the jurisdictional level of a province in one of those countries, but the impact of this policy decision, local policy decision, was felt much further afield than just that province. It had consequences everywhere, and there's this map from a paper in the New England Journal of Medicine from a couple of years later that highlights how the cases sort of spread out of Nigeria to go in all the region. Okay, there were also cases at the time. India was still producing cases. India has been polio free for quite a few years now, but at the time they were still producing cases. But the important thing is all these arrows that you can see here, and all these arrows come from this change in policy that took place locally in Nigeria at some point. Okay. Now, let me look at spatial aspects in animal diseases. I'll start with an animal disease that works essentially like we saw earlier with the plague. And so the when you think about wild animals, so what happens there is that the spread typically follows what's called a traveling wave pattern. And so what I'm showing you in the next few slides is the cases of rabies in Europe in 1990, 2000, and 2010. So this is 1990. Make myself disappear. This is 1990, and you can see that the cases, well, there's cases as far west as the middle of France, and things are spread out all over from the middle of France essentially to Poland and a bit more towards the east, but not so much. And then 10 years, that's 1990. 10 years later, you can see that the cases have moved towards the east, and 10 years later, the cases have moved further east again. Okay, so you can see how things have organized here. The wave is moving towards the east, towards the east. Difficult for me to understand that I have to move in that direction. So things are moving towards the east. And this is, if we can model that using what I call partial differential equations, for instance, there are some interesting works of Murray in the 90s and so on about rabies, and you you can really see this wave moving through, and this is somewhat similar to that example that I was showing you earlier about the Black Death in Europe. So there's a slow moving wave that goes through the, the support, the geography. Okay. Now, if you think about livestock, the situation is more complicated because livestock are typically tied to humans in a sense, and their movement patterns, if they have any movement, their movement patterns are more similar to what humans do than to wild animals that we just saw. Okay, and so now I'm going to sort of show you two examples, one of them being foot and mouth disease and the other being avian influenza. So first of all, foot and mouth disease. Some of these figures you've already seen in the introduction to foot and mouth disease and so on, but I'll take them again. This is a pool of foot and mouth disease of serotype O. And what you can see is how it is spread spatially. Okay, so these are the different subtypes, let's say, of a pool, and where they are located. In terms of spread of foot and mouth disease, this is the framework that the FAO the European foot and mouth disease and the WAHO use to describe how a country may move from being endemic with foot and mouth disease to not having any foot and mouth disease. And so you can see here, stage 0 is the worst possible stage. Foot and mouth risk is not controlled. There's no reliable information as well, because this is something that is quite important, but I discussed very briefly when I was talking about bovine tuberculosis, but the idea is the same here, to be able to do something about the problem, you have to know that the problem is there. So if you have no reliable information, you it's not easy to take any decision. Okay, so to move from stage 0 to stage 1, a country must do a comprehensive study of foot and mouth disease. It must have planned a comprehensive study of foot and mouth disease. Um, then So at that stage, we've identified the risk and the control options. And you can see that, okay, a country may move up this ladder, let's say, as it makes progress on understanding and controlling. So you can see stage 2 is implement risk-based control. Stage 3, implement control strategy to eliminate circulation. Stage 4 is maintain zero circulation. And stage 5 is maintain zero circulation incursions and withdraw vaccination. So because while you're moving up, you will have to vaccinate, but when you are free without vaccination, it is that you've achieved control of foot and mouth disease without and you don't need to vaccinate anymore. And this is, yeah, how you progress along this. And when you've reached stage 5, you can apply for a status that says you're free without vaccination, and if you are, well, that's good. But that means every country is somewhere in these stages and trying to progress typically up the ladder. Now, this is an example of the timeline of appearance of foot and mouth disease of type O in India, and then how it moved from there onward. So you can see that there is a progression. I'll show you a map that shows not exactly the same information, but a bit the same idea. This is how the foot and mouth disease has spread in the old world. This is another source. Um, this is not as detailed and it doesn't have a timeline per se, but you can see what's in there. Now, the 2000, anyway, in 2001, there was an outbreak in the UK that I've already mentioned in the introduction, but this outbreak was extremely well monitored. So there is a lot of literature about this outbreak, and if you're interested, if you're looking for data, some of the data is available. So I've taken a few papers, and in particular this one, which is describing the epidemic in the first 5 months, so by Gibbons et al. So this is published during the epidemic itself, or I mean after, I think just after the end of the epidemic, but on the sort of the same duration, same time period. So this is what the epidemic looked like in the UK at the time. You see that there's several what they call groups, which are places, so clusters, local clusters essentially of cases. So a few in Wales, a few in southern England, northern England. You can see that group had a lot of cases. So this is just showing you the farms that had cases. And This is something that will come back to when we look at foot and mouth disease models with spatial aspects. It is that, interestingly, the way people modeled that epidemic, I mean, they had started doing this before, but they continued using the same type of methods, is that the focus was on the farms, they call the premises. Um, and so this is the epidemiology, the epi curve of the number of premises that are showing symptoms, or well, I mean, that have animals showing symptoms. And you can see this looks very, I mean, this is not a number of infected, it's the number of infected farms. But that curve looks very much like an epidemic curve if you were looking at the number of infected instead of looking at the number of infected farms. So essentially, this is telling you, well, you can do the same as you're doing typically in epidemiology and just think of these as infectious individuals, but the individuals are the farms. And if you look here, this is the same information essentially, but where cases have been split between what they call local and non-local. So a local case uh, is one which happens within 3 kilometers of an, a case that had already taken place. Okay, so a local is probably local infection. These are the ones that are in orange, and non-local cases are the blue ones here. And you can see that most cases were actually local. So this was transmission from an infected farm into a non-infected farm within 3 kilometers from the infected farm. And this is the foot and mouth incidence. This is the cumulative incidence over the course of the epidemic. So you see that really where most cases happened was in the north, and then there were cases a bit everywhere in the country. I mean, it's important because that spread was not only confined to a cluster in the north, but also to various other places. Uh, this. And now, one of the things they had was movement information because cattle and livestock, I mean, livestock in general, but cattle and sheep and pigs who were also infected are relatively well tracked in terms of how a herd, animals from a herd are sold to another herd, and etc. And in a way, it was fortunate uh, that France and the UK had the mad cow disease in the in the 90s, late 90s, because of that disease, there was a lot of work done to implement what they call traceability of meat. Um, in both countries and in the rest of Europe as well, but in particular in the UK and in France, they had this that they put in place, and so they knew really well how the animals moved between herds. You had to be able to document the location of the animals, and that means that what you can see here are movement of animals. So remember that this is where most of the cases were originally, but you can see how some animals went from one given place to another place. Okay, and this is so movement before the 23rd of February, at which point something happened, which I'll go through in a second, when people realized that there was really a big problem. The movement of cattle, livestock was restricted. But that's prior to this. And you can see how, so these dots here are infected farms, and you can see how they sort of sprung up from the movement of animals between the different locations. This is from another paper I can't remember which one it is at the reference, but it is a timeline of the epidemic. So you can see early February. That's when they estimate that the disease entered the UK. 19th of February, the first detection takes place. 20th, that case was confirmed. And on 23rd, they started cutting on infected premises. So remember that this was movement prior to the 23rd. Um, and this is when they started cutting. Uh, then IP is infected premise. So on the 15th of March, they started cutting sheep which were close to Lockerbie. Um, and then they did contiguous premises, etc. So here you have, and when you can go to the slides, you have a timeline of the epidemic, and you can see that the 20th of June, so said what 4 months later, 20th of June, that's when there was the first day without any new reported case. Now let me switch to avian influenza. So avian influenza is even more complex, I would say, typically than foot and mouth disease because, and I talked about this a little bit in the introduction, it's a disease that involves multiple bird species, and it involves both wild and livestock birds. And interestingly, birds fly. That means that additionally to this aspect we just saw in the foot and mouth disease, where we have livestock that are moved between farms when they're sold or when they age into production, etc. Here you have that component that exists as well, but you also have wild animals that can carry the disease from one place to another. And birds go far. So this is migration routes for birds in Middle East to Europe and Asia and Africa. So you can, this is a graphic I already showed, I think, in the introduction, but this is interesting because you can see all these animals, all these different bird species that are moving across. And actually, it's funny, I don't see here. I know that in when you're in Morocco, you see storks, and they're coming from France, and I mean they go all over. You see them in France, you see them in Spain, and you see them in Morocco, and they're the same animals. So it's not only that way that they're going; they're also going that way. Okay, so animals move along, and this is another graph that I showed you last time. The interesting thing is that there are different types of interactions that are possible and different species involved in the different types of interaction. So what you can see here, we have some wild birds, sporadic transmission towards these are these are species in which transmission is sustained. Um, these are farm animals. Uh, these can be farm or not. Uh, and then there's the sporadic transmission potentially to humans or swine, which is one of the big fears that avian influenza would combine with a pig type influenza and become transmissible. Okay, so what's important here is that there are these different spatial scales. So these livestock, poultry typically is not very mobile, but it's coming into contact with um, related species that are more mobile, and then other types of species. And all of that means that avian influenza essentially has an almost global reach, um, and the capacity to go much further. In terms of the history of avian influenza, this is from a paper by Lupiani and Reddy. I think I mentioned that paper earlier. I actually might have shown this table. Uh, the first time that avian influenza was detected was in 1878. They call it foul plague. Plague is sort of a generic name for something that goes bad. So it was called foul plague, and then they re-identified. Um you can see that the identification of a highly pathogenic avian influenza, the virus, that dates from early 1900s. Then there's a variety of influenza types and influenza um, strains that were successively detected and taken as the sorry, the case that's going the next disease of interest. And just to illustrate this, this is a paper in PNAS from 2006. At the time, H5N1 was where we thought that the main problem would be. And I've taken a paper that looks at the global spread of this particular strain. Here you can see a phylogenetic tree. This is showing you how the different strains evolved within that H5N1 um, substrains, and how things evolved within that H5N1 strain. Here you have something quite interesting. So it's showing you how what type of spread took place. So for example, here what this is showing is that there are this is migration because of migratory birds. Okay, there's poultry. So this is, for example, Russia selling, well, some people in Russia selling some poultry to people in Kazakhstan, whereas this is migration. Here, this is migration, poultry sales, and then some of them are unknown. These are, for example, this one is unknown. And this is also the contribution of the different pathways. Okay, so you have the wild bird trade, you have migratory bird, or poultry. And so depending on, so here you can see, for example, all those transmissions here are stemming from principally migratory bird. But for example, in Spain, here it's mostly wild bird trade and poultry. So things spread that way. And so the authors tried to estimate, for example, the predicted risk of H5N1 introduction from countries that had H5N1 cases. So this is showing you essentially a risk map for different countries in the world. Then 2009 pandemic happened. The strain that was at the time was H1N1, not H5N1. And actually since the strain that seems to generate some concern, well, I mean, there's several strains, but is H5N8. And there was a spread event in Europe in 2016 and 2017 of H5N8. And this paper here is documenting this particular spread event. And so you can see here the spatial distribution of the outbreaks of H5N8, and things are classified in terms of whether things happen with domestic birds or wild birds. I come from this area in France. We make a lot, I mean, they make a lot of geese and ducks, and clearly here it's domestic birds that were mostly affected. The other cases are typically more wild birds. And there's some spots also with a lot of domestic birds affected. This is the timeline of the spread, still with the same color code in terms of domestic versus wild. And so you can see starting in October, not a lot of cases, and November, December, January, February, March, etc. This is the outbreaks in Europe, the different countries in Europe, how many domestic birds and wild birds were detected, uh, and when the onset of domestic bird was first detected and the onset of wild bird was first detected. Okay, so you can see how many cases there were. They were pointing out in France there was quite a lot with domestic birds. There's also Hungary that we saw so having quite a few domestic birds cases detected. And this is the percentage, number and percentage of domestic outbreaks of H5N8. Um, and so, for example, in France, the size of the farm, okay, so this is how many animals they have, and um, yeah, okay, so I'm not going to go into details here. Um, One other thing that I wanted to show is this paper that is in Science um, in 2016, again H5N8, but here they're considering in particular migratory wild birds. So this is this component that I was describing earlier, where avian influenza is spread into poultry farms by wild birds. And so here this is a paper that investigates this component here. And they produce maps such as this one. This is the world seen from the top, essentially. Interesting projection here, but which is saying, uh, which is showing the transmission routes um, at different moments in time. You can see 2014, April, August, November, and January 2015. So these are the different contributors to spread, domestic or wild, and whether they were moving, wild long migrations, long range, or wild short range. And that's it. So as you can see, there is quite a lot to say. That's why I didn't want to make a single video, because there's two of us coming up. But space is really, really important. And this is something that not a lot of people necessarily take into account, whereas I think it is a very, very important component of the understanding of infectious diseases. And in the case of livestock, this is particularly important. For instance, as we've just seen with avian influenza, this combination of wild animals that have essentially free range movement and domestic animals that are set in places but are also sometimes traveling between locations because of sales and for example, little chicks will be kept in a given type of farm for several days and then they'll be moved to another type of farm. Typically, this is organized, this happens all the time.